So that sentence caught me, that 2 or even 3 generations to make a serious impact. So I've known hydrogen since early 80s, 81. That's getting into getting into the 2nd generation. So I hope we can speed things up. I just found that point made by Finston at the time, and looking at alternatives and what makes sense, what not, is important. But it's not always just the technology that I was looking at. It's how can you green the system? How can you green the supply chain? And actually look at the whole system in totality, but then going with a deep sort of physics base as well into that system. And then I'll share with you, which is shown by this figure, which we published quite recently, as a matter of fact, just last year. And the idea was quite simply, how do you describe the system beyond just using simpler methods, but actually taking the tools of our trade, which we all know. So I'm just speaking to the converted here, and doing detailed process simulation, not just on a plant, but actually doing it on a system. And system, in this case, we selected PVs. You know, at the time when I was at Melbourne, mid-2000, I actually wrote a letter to Rudd, and I asked, hey, why didn't you, and I was coming from outside with the European passport, so I probably had no right to ask that, but why don't you just export sunlight in the form of aluminium bars or whatever, but using a PV infrastructure, and etc. That was early 2000s. So that's also getting 15 years on, and that's really a great opportunity also for Australia. But anyhow, so we looked at the system and looked at the whole production cycle of PVs. Specifically, as I was a director in the Helmholtz Center, which is pretty well known globally, but there's a very strong PV group that was looking at, was sort of pushing the limits of PV efficiencies, sort of electricity production efficiency. And so they were really on the forefront. So we got together within the Helmholtz and we said, okay, let's look at different PV designs, future designs, perovskite designs, or tandem type of cells, and to see what is the true recyclability of this, and what is the real footprint of the green energy we're creating, going from the primary, secondary manufacturing infrastructure and the recycling back. And I'll touch on this a bit later on. The message quite simple. We were looking at energy and materials as energy flows, but also looking at the quality of energy losses from the system, which we as chemical engineers and metallurgists also know is a more an exergy-based approach to actually look at the quality of material degradation by product design, etc. And I will get to that a bit later on in the lecture. So, and we've also been pushing that. I'll show to you just a paper got accepted yesterday on metallurgical thermodynamic rarity of elements. But so it's been part of sort of this analysis. What is green? And if you are then looking at the supply of metals on a green infrastructure, as green as it can get, obviously, you're always constrained by the technology and mass and heat transfer, etc. But that was the idea, and so we analyzed that, and I'll share a few results from that, and taking cognizance as well. And this is making the link also to minerals, and taking all those aspects together. As you know, we published this many years ago, this metal wheel, trying to explain to policy in Europe. Be careful, don't destroy the hub of metallurgy, which is the base metal industry or the steel industry. You need it to produce all the other metals. It was prophetic 20 years ago to actually, at that time in Holland, zinc was coming under attack. And they said, well, if you're killing zinc, you're killing indium. And well, shortly after that, we had the touchpads, which was using indium. And through Osmelt, we were recovering actually the indium from the slags by the TSL technology. So it all sort of came together, and sort of the baseline was, you need metallurgy, you need to understand that well, you need as clean technology basis you can get. And I believe Australia is a leader in that aspect. So that's the strength. And then also we've expanded that. This actually was a review paper in Materials Review, where we looked at the limits of circularity, but also the opportunities of circularity. And so we, over the years, we've redrawn the metal wheel, but to looking at it more from a OEM point of view. So if you're designing a part, what effect does it have? What is the true recyclability of that product? So looking from the primary side, going to the secondary and bringing the worlds together. But you can read all of that stuff in the papers. So this message we gave through 2019. I was part of an EU project called Socrates, where we had 15 PhD students part of this, looking at sort of closing the loop, using the usual buzzwords, but trying to make clear to specifically the European policy with the Leuven colleagues in Belgium. We came up with this, obviously them being bicycle mad people, also cycling, etc. So we came up with this, taking out a segment of your industry, you're buggering up the system. And this is the figure then we came up in a policy brief that actually went to the EU to make sure that there are good policy decisions. So if you're looking at the big picture and you're looking at the supply chain and understanding that you need the hub, the center, I call it the ball bearing of societies, to have that presence so that you can not only produce from primary resources, but also understand the metallurgy to recover metals from the secondary resources. And that's really a key message, putting metallurgists at the ball bearing and at the heart of circularity. So what we were trying then to do over the years was actually looking at these tools. How can we bring them together? And a few recent PhDs, you can see also the recent paper also by students and colleagues we did. And we also did a chapter in the new treatise of metallurgy, which will, I think, appear next year, actually showing this and actually analyzing metallurgical systems and large systems inclusive of product design, etc., to bring it all together and bring our tools and our know-how that is sort of key, which also your center of excellence is obviously also a nucleus of actually bringing that knowledge and maintaining the knowledge, advancing the knowledge to a wider community. So just bringing these tools together in a way that you can use them well. I know people use Aspen, they use other MetSim or whatever, but I got involved through Autotech, through HSC Sim. We linked exergy analysis, LCA analysis, etc. With methods of bringing in FactSage, everything, bringing it together to make sure that we can really look at very large systems. Large systems, I mean, looking at a product and then looking at 200 reactors, even more. The largest models I did in HSC were 220 reactors, or larger units, not all the pumps and all the stuff, but just looking at the major flows to make sure that we get and understand the true degradation of material quality in the system, but also energy quality, to therefore get to the bottom of what is a clean supply chain, what is green copper, green zinc, or whatever you like to call it, and actually show them to policy, hey guys, you have to be careful, you're killing the system with policy if you don't take care of what's going on in each step and in the whole supply chain. But so I used the buzzword of digital twin, but in my career of close to 40 years, well, I just called it simulation, but anyhow, that's another discussion. But you need a fair bit of stuff to come together, and this is what we what I still do. It's what I'm doing at the moment is these 2 weeks in Freiberg, teaching students this type of stuff and bringing it together. Obviously, not forgetting that ultimately we have to somehow link it to the sustainability goals, which have got other parameters. But that's a nice challenge to bring those worlds together. And we're doing projects at the moment here, which I'm involved in, to actually bring it or also further develop these aspects with students. We actually submitted the EU project with pretty interesting companies in Europe doing this, but also linking to SDGs in larger constrained optimization type of frameworks. So coming back to this is what is SMS doing, and I'm just one sheet still on this. What is the learning copper plant? So learning from the steel side, but is the learning steel plant, which is actually automating from scrap right through to coil, which is quite interesting. So this is always in the back of my mind to do this. So looking at this in more detail, and once again sharing with you also very recent work. You can see at the bottom the reference 2021 was done by a PhD student, which I will get to later on, actually looking then at green copper and integrating hydrogen with that, looking at demand side of analysis, carbon trading and all this type of stuff to see how you can balance it and where does it make sense. And I'll get to some results a bit later on to show to you, if you're doing this analysis, you need simulation. Looking at hydrogen, you can also look at methane, you can also look at ammonia, and what does this mean if you want to green up stuff, and what makes sense and what makes no sense, and how does that interrelate to the power grid, obviously also the supply of other commodities, and natural gas obviously having its price as it has, so you need to take that all into consideration. But you can look at this reference by the PhD student Fritz Röben, who just graduated earlier this year, or mid of this year. So then looking also at the bit of the analysis point of view, and I'll show to you this as well a bit later on. If you have a lot of technologies in your palette, which all can produce green copper, what makes sense from a systemic point of view, but also from the energy infrastructure point of view, using hydrogen, ammonia, for instance, as a reagent, methane, the consequences on the production. That requires one to have detailed understanding, obviously, within each of these unit operations to do well. So I put this up front. So I showed you the primary production, and here more the secondary residue type production, having the usual sort of mix of reactors, which using power as well could be quite helpful, and actually analyzing that in detail to look at, well, why don't I then just use an induction furnace if I've got a very low carbon footprint for that, and then using a total refining furnace, for instance, to do the refining of, and then going to anodes, etc. But very interesting sort of combinations of possibilities that you can start looking at. Once again, I'll come to the result a bit later on. So what does this mean? And I bring this in because this is my link back to Melbourne. Being involved with the TSL technology, and I've been pushing the physics of this as well. We actually had a PhD defense just 2 days ago of a student that did a lot of this work here in Freiberg with this very strong computing power here in the Dresden area with supercomputers, with being a material science hub. So looking at the physics and the constraints between mass transfer, heat transfer in slags in this case, and very interesting, the work on the left-hand side actually got a best paper award just this year at TMS for made transactions, where we actually measured in metal, which is the right-hand side, Gallingstan, which is a low melting eutectic, which is a liquid at room temperature, and actually looking at blowing into metal. Usually people do CFD and they blow into obviously water, but here it's really metal. And then actually on the left-hand side is the simulation. So what I'm saying is, and this, I don't have to explain this to you guys, you all do this, but how do you scale then to this reality of mass and heat transfer into your models and scale it up, the circular economy route up to the policy, to inform policy on the basis of the physics that is possible. And I think that is the challenge, and that's what I'm showing with this. On the right-hand side, also showing a pilot scale of TSL, which is actually in Freiberg, built at the time not by Osmelt, but at the time by Xstrata. And it's standing here, and we actually looked at that in more detail as well. But so, speaking all of this stuff, I just want to make sure that we have that you know that this is grounded in this type of detailed analysis, which is quite unique. We actually did an overview paper on TSL quite recently with a few Chinese colleagues and also Belgian colleagues, where we actually put on, this is the state of the art of CFD modeling in TSL or vast melting type furnaces. And you can have a look there. So hopefully we can get the CFD and the sort of modeling community to advance from there, looking at multi-reaction systems. But so we went on and actually used FactSage in these models. And why am I showing this again is, okay, we're in an academic environment here at the CRC, or the ARC Center of Excellence. But we've taken that CFD and actually put it into detailed models here, this one for lead TSL, but actually using FactSage and solution chemistry to actually model this. Also recently published part of a PhD student. So once again, you cannot just do the system models without knowing this detail and also the detail within the reactors. Otherwise, it just becomes playing around with numbers again. So we've been trying to do that as well. But also taking this further to the previous case here, which was more academic and gleaning from the information of the CFD, actually the different zones, etc., was coming from practical experience, but also industrial experience, looking and smelling and then seeing, checking out with CFD, which is what I pushed right at the mid-2000s when I joined Osmelt at the time, and said, hey guys, we have to look inside the furnace. And at that time also CSRO had done nice work, Phil Schwartz and the groups there. But so we pushed this on, and it's now been going. We were pushing it also here in Freiberg, which is far away from the heart of TSL, the origin, which is in Melbourne, by the way, as you know. But we were pushing it with research funds, which we got, which we tweaked off from sources to make it happen, because this is not the sort of how shall I say, the type of work that is supported by the academic sort of reviewers anymore, because it's not sexy enough. But this is at the heart of circularity. At the time at Osmelt, I submitted a proposal 3 times, and it was always discarded, quite frankly. And the irony of it, I sat at the table of a president of a large company, and he said, well, this work needs to be done, but the ARC did just not honor it, which is not right, because ultimately the work I'm speaking about is governed by the mass and heat transfer and the thermodynamics at the interface, and we need to do that. And the community is getting smaller and smaller. So it's for me really worrisome. But one needs to get down to the reality to ensure that the funds that are made available by taxpayers really get to the place where it's really making a change. And I see also the FBI CRC, for instance, is a great example, which is actually doing that in Australia. which is nice. Really nice that I was still can be involved in that. So here we went one step further. We created an app where we actually looking. Remember, I showed you the tilting refining furnace, where you're actually predicting a ppm level, what's going on dynamically in the furnace after refining actions of oxidative or reductive type of operations in the tilting refining furnace. So typically shown here, you can give the input, and then over time, you'll see the time axis looking at the change of slag chemistry, and then also the ppms of the minor elements which you're trying to refine out from the copper. Remember, this is copper scrap, so it's bringing in certain elements into the system, which are not always the same as in the primary production. But nevertheless, these tools are there, and we're trying to push to the limits of physics, so that, true to the message, greenness means you have to understand this in detail. And once again, one of the really great places, as you well know, where this knowledge is being created is Queen's and Uni, where this information, among others, comes from. And it's so nice to have these kernels of places where this knowledge is being preserved and continually developed, so that we can develop these models. In this case, FactSage, Python, ChemAppy, etc., linked together in a dynamic tool. Also going to HSC, I'm not going to go in this detail. This is just, once again, using FactSage, HSC, and then actually doing predictions, in this case for TBRCs. Same for tilting refining furnaces. So we've got really detailed models of this, all based on the physics that I showed previously, to actually do the designs, but also doing the predictions in future. A very interesting other one is also looking at dynamics. And this paper we actually presented just 2 months ago, November 2022, say 2 months ago, looking at autocatalyst recycling, actually having a dynamic scheduling model that actually looks between submerged arc furnaces, TBRC, and looking at this in dynamics. And I'm just sharing with you one example here, just looking at the PGM process value on the site in the different slag dumps that are around. And just as an example, then to optimize the system as a function of, obviously, the autocatalyst feed composition, etc. So once again, if I'm speaking about greenness, it's not just about steady states, it's also about dynamics and actually looking at the models that can be done. So all stuff really done in the recent time, at least I was involved in trying to push this last 2, 3, 4 years. And yeah, for me, extremely, I'm now getting close to 64, but I think I've never worked as hard as I have at the moment, but in a sort of energizing way, because we can bring all this stuff together at the moment. So then coming back to this example, so I've shown you the original figure, but then gone to some detail to show what's behind the icon. It's not just a little picture, it's detail. And then ultimately looking, and this is a busy slide, but you don't have to look into all the detail, but actually looking at, in this case, the exergy efficiency of refining, of using materials, reagents, looking at the exergy dissipation through dilution, and actually not just looking at the normal LCA, I call it the cookie point methods, but actually looking at the physics within each reactor and understanding the dissipation of exergy from it through quality degradation of materials, energy degradation, and therefore understanding what makes sense and what does not make sense. Obviously, using the suite of technologies which we are actually have commissioned over the years, and actually are, I cannot say much more at the moment, but I showed you some of them that are actually being, already in the public domain, but actually understanding for clients what makes sense and what doesn't make sense. And as I said here, specifically looking at the exergy efficiency of not just carbon footprint, we can do that, that's easy, but actually looking at the exergy efficiency from different routes. In this case, also excluding the exergy dissipation for creating the hydrogen from the footprint of the energy infrastructure in whichever country this is. But I leave this with you, and you can read this in the article in the proceedings of Cobre 2022, which was just, as I said, a couple of weeks ago. And coming back to this example, I'm just showing you the result. Looking then at, on the one hand, electrolyzer capex. There are different electrolyzers which you can use, solid state, polymer, or alkaline. The student actually looked in the context of primary copper production, and also looking at the direct CO2 abatement cost. When does it start making sense? At which carbon trading price? So while I cannot say much more, but this has been taken up by a large company somewhere in the globe, and actually looking at it. And this is the type of analysis based in good understanding of copper metallurgy, then looking at integrating different types of electrolyzer technology and seeing when does it make sense. And so this is the paper you can read. As I said, it's Journal of Cleaner Production, which just appeared just last year. So coming to more to the end, and hopefully I'm not speaking too much, George, but I'm now, I think, on
no,
35
please
minutes.
continue. I think most of us can stay for a little longer. Yeah, please continue.
Okay. So I'm coming back to this paper, and this is interesting. So this is sort of bringing it all together. So when I show the picture, also now specifically being in the industry side, but with this very strong link to academia, and creating also the detail to fully understand, is sort of in an OEM type of environment, what makes economic sense and not. And behind that is obviously the detail shown over here. Is here as a tandem PV cell, which is a mixture of silicon and perovskite type of technology. And looking at the left-hand side, it's a pretty complex mineral, if I put mineral into inverted commas. And it's got obviously flowing into it various metals and compounds which have a primary origin, then flowing through the whole flow sheet to actually create it and also recycle it or manufacture it. And you can see down here sort of a bit of manufacturing as well, then disassembly. Sorry, here's the manufacturing, here's the disassembly, and actually looking at that bigger picture, which you can then, obviously, you can go check it out in these conference or in the journal publications on this. And so they always said, okay, if you're now using this big flow sheet as a plant within the circular economy of PV, of this tandem type architecture, which has a higher efficiency, at least for PVs, and being sort of pushed by the developments, among others, at Helmholtz Center in Berlin, which are experts in these. So we got involved together and said, okay, now how green is all of this? And they were keen to actually look at it. And one company came on board and actually also helped a bit from the PV side. So what do we look then at? The same picture, and once again looking at the primary input, which is always there because you will always have losses. Looking at the circular economy and the different steps of it. Looking as well as at the sort of stakeholders that can play a role that affect the activities between these segments, which can be, among others, thermodynamics, or just physics, but also consumer decisions, which is how do you model that and how do you bring that into your equation, which is interesting to do. But at least just looking at it from a technology point of view as a big flow sheet, and you put this flow sheet into different regions of the world and say, okay, now we are creating green energy. We're going to create green copper from green energy, but so how green is the copper in the system? And this has to be openly discussed and shown. This is the background to this PhD work, which hopefully will be defended early next year in Munich. So we put this big plant, as you see here, and we put it into different regions of the world, as you can show there. So you would obviously then, and even if you look at the recycling aspect of it, it has an effect, but how big effect does it have? Kerf recycling being the residue created while you're cutting the wafers, and end of life recycling rate is shown over there. So you would obviously then do PV production in Norway with its low footprint. So, and then also looking at the life cycle cost of energy against these two axes. And then also looking at the footprint, obviously there's an optimum between the two. And so this fallacy of I want to recycle things 100% by negating second law of physics, of thermodynamics, of degradation, of quality of materials is nonsense, really. But how do you bring that message across? But at least the example here just shows, if you're speaking about green energy, then green metals, and then obviously you need to slowly work up the infrastructure to greenness so that we can globally get cleaner supply chains. And so this is what the real intent was over here. So please have a look in this paper, also recent resource conservation recycling. So let's get to the end. So how do you now look at that system, but looking specifically at the design? And I've shown this example in the past, but this work has gone on where we were looking at the design, the modular design of products. In this case, the openness of Fairphone, which is a small supplier, but very noticed also by the big players like you know, the one with the kind of fruit on it, and they know about this work, and actually looking at what is the limit of recyclability. Whatever you say, while some OEMs have on web pages very high recycling rates for this, but it's just nonsense. And once again, it's embedded in the physics of the system. And so the question is, how many modules of a product would maximize the metal recovery or the material recovery into the material quality required to go into the same product? Not down in the sense downcycling, but actually keeping parity of materials. That brings this discussion of exergy and material quality very strongly into play. And so in the last years, we've been really developing that to actually say, hey guys, what are we talking about? So, and to rattle this chain a bit, I was a bit naughty. And I not naughty in the sense, but just wake up people that if we're looking at a very simple metal like zinc, and we are recycling it. A company approached me about 3 years ago, the time just before COVID, just before I came to SMS. So I did this work for them, where I took the HSC SIM, which I'm still mentioned as one of the advisors in the tool, was actually pushing it. And we said, okay, if we are recycling zinc, and they had really nice smelted remelting technology with a very low footprint, and I knew that, and I said, well, if you're just going to measure this, the guys, are they going to believe you? So what we did, I created the model for them from the data using scope 1, scope 2, and scope 3, and I did the whole chain of zinc containing residues right on to die casting machines in the end, and looking what the footprint is. And so obviously you come to the point, well, you know, the footprint is rather low. Remelting zinc well, it's got a low melting point, so it's obvious. It's just a matter of the technology and how much heat loss you will have in the system. So we came to a very low zinc footprint. And this really started wakening up people. Hey, this is the footprint of recycling zinc. Then Boliden came up, and they have their green smelter up in Norway where they're using hydro power, obviously therefore decreasing the zinc footprint as well on the primary side. So here we've created a playing field between a rock and a hard place. Hey guys, we have to change stuff because people are going to start asking for clean zinc. Although the topic is clean copper, a green copper, here's green zinc. You can replace that. So we did this and we just compared what is in the databases and what is what is reality. And you can see there's a huge difference. So if automotive then would use zinc data in the Gabi database, or they would use what we actually calculated on the basis of a simulation model, with the real parameterization from materials with the chemistry and right on to the end, inclusive of emissions, etc., and the filter bag houses, etc. You come to different values, and so this is the playing field that is going to happen and needs to happen. So if you have green metals, green infrastructure, green everything, make bloody sure that it's green. And I know the ARC, FBI, CRC is doing this. I'm involved in Melbourne, was also involved in this. Now, getting back to the Fairphone, and this is interesting. So we got involved in this 5 years ago, and then in the COVID time, once again, we did this work, and it's well documented. It's online. It's on their webpage. So we got through redesign of the Fairphone by the methods also shown by the detail of zinc, for instance, which is a very simple example, but in a way also really complex in itself, because you have to really match that whole flow sheet in a very fundamental way. We could increase the recyclability from about 30% to 50%, which is quite significant by redesigning how you do the modules. Whereas online, you would say some of the companies are sort of flaunting these numbers. And I just say, is this the Excel mafia, or what are they calculating, or what are they basing all their calculations on? Reality is lower, but it's based in the good understanding of the system. These guys actually publish those numbers online, also shaking the industry because they know this. The OEMs know this. Very much like the zinc industry. So you have to use, from an academic point of view, these methods to actually just start shaking the tree to make sure that we come to good answers. Now, and I would like to share this also with you. This is also now really coming to a bit of fruition after about 20 years of pushing and pushing and pushing. So here we've got an EU project, which you can have a look. It's Treasure Project, but EU. And as it says, guaranteeing a sustainable use of raw materials in the automotive sector. Involved is Volkswagen / SEAT, which is the Spanish arm of it. Looking at automotive parts and looking at the recycling rate of parts and redesigning parts so that you can recover more materials at the quality. In other words, module back into module, not module back into park bench and then some magic trick of speaking about recycled content coming from wherever and then back into the product. No, module back to module, or into automotive at least. And so this is the key of this project, which you can have a look. And it's based on all of this stuff that I've been speaking about in the last 3/4 of an hour. So it's already happening. So it's redesigning parts, looking at the supply into the part from the primary side or the secondary side, redesigning it, and then looking at the recyclability, which is quite nice. That also the level of thinking is actually advancing to that level, that we're not just doing design for recycling, which is also a buzzword, on an Excel sheet and having some magic recovery factors. No, this is actually based on the total supply chain and the technology within that supply chain. And we've got a pretty large process model that actually does this. I guess, if I recall, it's over 230 reactors that are taking care of in some parts, over 200 materials. You won't believe it, but sometimes it's amazing how many tightly combined plastics and alloys and fillers and stuff are there. And then people say they're speaking about 100% plastics recycling. It's just not possible if you look at it in this detail. So this is this project, and we actually just completed the 18 months report, where we actually show we have many parts. SIAT gave us the full bill of materials because they're involved. The full mineralization, in inverted commas, of that part. Where is what situated? How can you perhaps dismantle it? So we looked at a part, recycle it, put it through the model, see what the recoveries are. Dismantled it further, which costs money, obviously, and time. So what is the recycling rate? And therefore, getting an insight, what will increase the recyclability by true redesign, but based on all the tools which you support in the Center of Excellence of COE Minerals. It's really based on that. And that is really, for me, a huge change from, as I said, the Excel mafia that's doing some calculations and boom, some answer comes out, which isn't really helpful. And that doesn't help for policy because it's easy to understand, whereas metallurgy, which is at the heart of circularity, as I started off with, needs to be feeding in to ensure that we understand those limits so that we can get the policy message right and to get away from utopian ideas. So this is a paper, let's say MDPI paper. Some people may frown on it, so usually I don't publish in those, but this was interesting because the special edition, you can see SIAT involved. We're looking at the criticality of these materials and a simulation-based approach. It just got accepted yesterday. You can say, well, these papers get easily accepted, but I think what's written in here is quite unique in the sense that it goes from the criticality or the scarcity of elements in environment and on an exegetic point of view through a simulation model, which is simpler than the one in Treasure, but actually pushing it through the system and actually looking at the detail, really the detail of the limits of circularity, the limits of recycling, understanding the degradation of quality of materials, etc. But as you can see, SIAT is involved with a few Spanish research organizations that are knowledgeable in the field. So to end off, and I always show this picture. So this is a picture that a student, Alejandro Abadía Flamatz, he's also a Spanish guy, but a bit of a link to the Spanish people at the moment, or had for a long time. So this sort of summarizes the picture. We're looking at energy flow, but we're looking at material flow, all in kilowatt hours per hour. In other words, kilowatts. We're looking at exergy, dissipation, kilowatt hour per hour. We're looking at degradation of and dissolution of elements in the wrong places, and then we have to unmix them. So, but what is very clear from the figure is it's a downward spiral, and so all we can do with our knowledge is to mitigate that spiral and that slope downwards. And so this is, we've been propagating that for some time, but of the years, actually starting, quite frankly, in Melbourne, or even before at Delft at the time, we started looking at exergy as a measure of understanding circularity. We've built that into HSC to actually, I had exergy put in, and I remember we had a pizza in Melbourne, I can't remember where, at the time with Odotech, when just after they took Osmelt over, I sat there with Antti and I said, hey, Antti, we have to have exergy put in so we can analyze this system. And it's taken obviously another 12, 13 years to get here. But it's taken time to look at that detail. But so we are mitigating, we're trying to mitigate that. And interestingly enough, this journal has actually got that picture as the sort of governing light of the Journal of Sustainable Metallurgy, and actually getting that message through. Hey guys, this is, if you're doing research, understand how we can mitigate that spiral, which is inevitable part of our life. but we have to understand that well. And so that's quite interesting. And it actually, that picture, the student and I, we sat in my office here at Helmholtz in Freiberg, not far from where I'm sitting now. And we drew this and we said, okay, this is the message that we have to get out. Of interest for you as well might be the following, is this Sustainable Critical Materials is a MOOC we did, funded by the EU. At the time, I'm not so involved at the moment, but it was looking at criticality of materials, which, you know, you can speak about criticality and this and that and write nice reports, but in the end, you have to make it happen. You need the metallurgical infrastructure to make critical materials not critical, because if you don't have infrastructure, everything's critical. And people don't seem to understand that. So it's nice writing reports, but goodness, we need the reactors as well to make it work. So there are companies that also rattle the chain. So I did this interview with Arubis, world's largest copper recycler. Well, we have a very provocative title where briefly the messages that I discuss here are discussed. You can go online, you can read it there. It's in their year report. It's already a bit dated, but the message is not dated. It's the year report of 2018-19, our financial report at the time. So we're also writing this book where, okay, it's been, we have already the handbook of recycling version 1, now it's version 2. Hopefully we'll have this out in the first quarter of next year. So sickness, illness, COVID, everything has delayed stuff a bit. But we've got most of the chapters in where all of this that I'm discussing now, we've advanced from the first version, which I still was involved in writing at in Melbourne at the time still. We started with the Handbook of Recycling version 1 about 2011. So it's also got Australian roots. I just wanted to share that with you. But now we are already at this, 10 years later, we're at this version, but hopefully we'll get that out soon for your information. But anyhow, so I just end off with this sort of, and I sometimes do this because of this downward spiral of stuff. This is this Sintra's mystical inverted tower, and I've shown this perhaps to 2 or 3 people have seen this, but I always show it because it's also got a bit of a, how shall I say it, a philosophical deep base, because circularity is not just technology, it's also philosophical, I think. That's for me another discussion around a beer, George, when I come to Melbourne. But anyhow, so this is a downward spiral of our society in a sense. So, but you can look at the deep dungeons of the darkness, but you can also look at the light from the bottom up. So I tend to look at it from this point of view. So how can our community, which I think is key to a circular society, Australia plays such a key role in this, because most of your processes are clean, they're at the highest level. How can we as a community play a role to mitigate and look at clean supply chains and make them work? For that reason, I always have maintained my link to Australia, because I feel there's so much to be gained from this, because you have very concentrated knowledge base on these things, whereas sort of Europe is starting to get a bit depleted in that respect. Well, we're trying to do our best. I do this course. I have quite a number of students, but we have to stand together as a global community to make sure that metals, wherever they come from, are as green as they can get, so that we can look at this bigger picture and give credence and honor to the word green, what it really means. Green relative to what? Net zero relative to what? To answer those types of questions. So I think I've now, I was allocated an hour, so I think spent exactly an hour. So I've left little time for questions, but my breakfast is only in an hour or so. So if you would like to ask a few questions, I would be welcome to try and answer them.
Fantastic.
Thanks for listening.
Thank you very much, Markus. Fantastic. I think a number of us can stay and have discussion for another 10, 15 minutes. I mean, if some people have to leave, or I understand that, but we do have plenty of time for questions. And anyone want to kick off? Just unmute yourself or raise your hand, either way.
Yeah, George.
Peter. Yeah.
Marcus, thank you. Really, really nice. I had a sort of a semi-philosophical question. I worked on a thing called water productivity for a large number of years. And it turns out that if productivity is actually truly increasing sustainability and recycle and reuse and better use, the number of things that truly change productivity turns out to be very, very low. It's a really, really tough problem. And in the context of metals, and you show these circular pieces and you know, with hydrogen and everything coming on board, what is the, and you also showed, I think, very nicely that crossover point in recycling where you can go from module to module is probably no better than 40 or 50% in the best of cases at the moment. Yeah, what is the game changer there? Is it 10 things, or is it 1 or 2 things? Is it a big change in energy? What would you call CO2 input? Is it design? Or is it just a whole range of things that you just have to improve in a whole range of areas to really improve it?
Thanks, Peter. That's a very good question. It's one that I've been trying to answer a bit of my career, and water is a beautiful example as well. But just keeping it with the metals, you know, there's always been this hype. So a lot of people say design for recycling will change the world. It's not the case. You have a functionality which you have to achieve. So by default, materials are tightly connected. By default, therefore, recyclability is always going to be limited. So what can productivity then improve if you can't unmix the complex mixtures? Then obviously the power mix plays a role. Obviously, if we have an infinite, we heard yesterday that fusion has seemed to be starting, they've managed something in that sort of arena, but still you need to unmix the complex mixtures, and still physics determines that. Just like water, you'll have to, if I may use the analogy, you'll have to remove the contaminant cations and anions, which is not different to what we have to do with metals. So the whole discussion that I'm constantly trying to have, there is an optimum somewhere, but to falsely say that I've got 100% recycling is wrong. It's patently wrong. But unfortunately, it's a nice message, and it's a feel-good message. And so how do you explain that you have to change a lot of stuff to get it right? And ultimately, so to answer your question, you need to look at it from a system point of view in each. If you don't have a system model, you can't understand which buttons which would have the most effect. So once again, for PVs, what is the button? It's create a green infrastructure, green energy infrastructure. Quite simple. You can recycle and gain something. You can redesign, you can gain something, but you need to lower the footprint of your energy infrastructure to get the CO2 down, to have green elements, green metals, to have a green product. So, but each case would be different, obviously. And so I always have the analogy, which you may have read it, Peter, which relates to, I think, your water. As you know, I did that United Nations report on metal recycling while I was still in Melbourne. And I have a case where I just say to people, and it's being used also here in Europe, I start seeing, but unmix your cup of coffee of yesterday and create a beautiful cup of coffee with the same aroma, same quality today from that trash of yesterday. That is the question. And it's all about quality. How do you maintain the quality? How do you capture the aroma of a coffee of yesterday and actually, like a genie, just put and keep it in the cup so that I can savor it tomorrow. So it's a differentiated discussion. So if I have a park bench or I have a wooden bench, obviously it's beautiful, recyclable, cradle to cradle. But those are the type of beautiful examples everybody feels fuzzy and warm about. Then I take the telephone. For me, the question is then as well, how many modules will increase the recyclability to the maximum possible way so that it's still economic, which is relatable back to the first and second law of thermodynamics, ultimately, rather than just hacking it to bits, to zillion bits, and then salting it, which is also stupid. It's just crazy. That's also still hacking cars to bits and telephones to bits, and then sorting and using all kinds of fancy sorting equipment, which is nonsense in a way. So it's, for me, the question is for a complex product, then to answer it more specifically, how many modules will maximize the metal recovery by still being economic? And that requires detail of understanding of each module to get that answer. So a long answer to your question. So really, in summary, there are many answers, but you have to understand the system. You have to understand the mineralogy, because that determines the whole system performance. And then, understand it on that physics basis, what makes economic sense and what not. But that's what I've been trying to do for a long time, but I don't think sort of policies sometimes gets it. But I once had a discussion, I think Robin, if he's still on board, he said, well, Marcus, you have to set this down into 3 points so it's easy to understand. I'm still grappling with that question, Robin, if you're still online. But I do believe, and I'm trying to teach this to younger people so that they carry the message and go out there to actually show this detail and the fallacy of preaching this utopian, we can close the loop nonsense, which people are doing. So, yeah, Peter, it's a bit of a fuzzy answer, but I hopefully with the presentation I've tried to touch on that. And just think of your cup of coffee. That's for me always a very pertinent discussion.
I suppose ultimately in all of those circles, there's a little piece that there's some material that you just can't get back to where you needed it. And as the water analogy goes, there's a bit that I call society's ills that you probably have to destroy. And people say that you can't do that in a circular economy. And I say that is actually part of the equation if you can't design it out.
I totally agree. I actually showed this example to students just last week. When I do the simulation, I take aluminium. Aluminium is a nice reactive metal. It creates oxides, obviously dross. It can react with carbon or phosphor, sulfur, etc. And that's the ultimate residue. And I said, hey guys, we are recycling aluminium. Firstly, we have to dilute out the contaminants, which is primary energy. And secondly, we have ultimately this residue. We have to deal with it. And it most likely goes into a dump because I can't unmix it. It's exactly the same message. But we have to teach young people to see that. Excel doesn't help. Simulation is the only way to show that you will create compounds which just cannot be unmixed or cannot be reduced back to primary metals in a reasonable economic way. That matches your stuff. And that's what I'm teaching the students here, to just take that message out. Hey guys, speak the truth.
Kevin, do you have a comment? Question?
Yeah, great talk, Marcus. Really appreciate you contributing to our signature lecture series. And yeah, unfortunate about the technical hookup or hitch at the beginning, but we got there. My question is, what are the pros and cons of, say, low temperature pathways versus high temperature pathways? Or is it all going to likely be high temperature?
Given, I get that question often because it seems to be that I started off with the pyro side, but I was trained in South Africa, and my first job was hydrometallurgy of gold. So so that is my origin, minerals processing and gold metallurgy. Now I have a balanced view on that. And although I showed a pyro heavy upfront, and that was probably not intentional because it's just where I am at the moment. For me, there's always a balance between hydro and pyro, pyro, hydro. And you know, a couple of years back, you know, one of the real drivers to get exergy into HSC was for me to understand, is it better to treat e-waste by hydro and then pyro, or pyro and then hydro? That was for me one of the questions I wanted to answer. And the reason being, the plastics part of, say, e-waste, if I keep the answer very complex, are very simple to a very concrete example. So if I'm doing, say, hydro on e-waste, I end off with some dirty plastics, which is actually toxic, which is your leaching is never 100%. And so what do you do with the plastic? So you'll obviously have to combust it. You once, as Peter says, you'll have a residue in the dust or flue dust, or you'll have a slag or whatever. So if you look at it from an apples to apples discussion, to answer your question, and I'm not going to give an answer, but I analyze the system, and it depends on the e-waste type and grade and what the plastics are. Do the hydro, then do the electrowinning, and then do the energy recovery from the plastic combustion, because you have to do something. You can't put it on a dump. That is circularity. And then look at the exergy dissipation from that system. And then you do it the other way around, where you say, okay, I'm taking the plastic. I'm not now using electrowinnings kilowatt hour per ton, but I'm looking at electro-refining kilowatt hour per ton, which is much less. But I'm using the energy and the dissipation of exergy, which is once again a function of how much plastics are in the e-waste, and you take it through once again to cathode copper. And that is a simple example that I use to answer that question, but it's a case by case, where perhaps the one is better than the other and vice versa. But I've got no clear answer to that, other than one has to analyze the system very carefully to ensure that you're not creating a secondary and a tertiary residue, which then will cost money. Might not cost money in certain countries, but it may cost money in the future. But to hide that in the analysis is no good. You'll have 100 units coming in, 100 units coming out, whatever they are. And understanding, not in terms of just CO2 and LCA, but actually looking at the quality of residue that I'm creating and what can I do with it? And what is it ultimately? And is it safe? Is it toxic? Is it not toxic, etc.? Yeah, that's a long answer to your question, but I've looked at that very carefully. And I once presented the results in a hydromet conference down in South Africa a couple of years back. And you'll be surprised how much exergy is dissipated in the hydro system as well, looking at it very carefully from that perspective. But no, it's also in short, I've got no preference. I just look at it per case by case basis. But I have a balanced view on hydro and pyro, hydro, and minerals processing, modular design, and looking at the minerals processing front end to see how that affects the downside. How does the redesign of the module, for instance, if we stay with e-waste, which is the circuit board, if I can redesign that, would then hydro be the better option than just burning the hell out of it, and with its big capex? And by the way, there's now a project that has also been approved, like the Treasure project, that is actually looking at circuit design, in electronic circuit design, and how we can optimize the recovery. And therefore, it begs the question, is hydro then better? Because you've now concentrated stuff in a way that it makes more sense to do hydro instead of pyro. So it's interesting stuff, and my contribution will be exactly to try to answer that question, not just to put the hammer of pyro on top of it, but actually using perhaps the more sophisticated hydro up front.
Do you think that?
Sorry, Kevin.
I was just going to say, do you think that that we're at thermodynamic limits already, and that the real gains are more around process intensification, which is maybe in hydromet more selective ways of pulling what you are after out, more selective?
Yes, yeah, sure. Process intensification is obviously always the case. That's why I also showed the high temperature mixing and CFD, because that's also intensification. But if you then look at the hydro side, where, okay, going through the pyro side, it's a big hammer. Okay, you're pyrolyzing and doing what you're doing if you remain with e-waste. But if you're going to e-waste, but you're selectively recovering certain elements, and I discussed this with Jacques Extend just the other day. I've also got a close connection to him, being my ex-PhD student from the past, using glycine, and I think perhaps you are referring among others to that. But then what is left is also the question: how do you deal with what is left? You can pick out certain stuff, but if you look at the plastic and you have fillers and your flame retardants like bromine or antimony inside, how do you deal with that bit, which your lixiviant won't get to? Then you have to fine grind it, but that's going to cost energy. It's going to create dust. The gold is going to smear off in the grinding. So you have other secondary losses in the system as well. So if you are going that way, one once again has to be very careful how you analyze that system to ensure that you're not creating a secondary and tertiary waste. Because I always say the plastic's got bromine in it. How do you deal with it? It can have antimony oxide as a flame retardant. How do you deal with it? Your glycine is not going to get there. But anyhow, but I agree totally. One has to look at this, and by all means, you can cherry pick out the right stuff, but look at the rest that's left behind.
Thank you very much, Marcus. Yeah, really nice discussion. And yeah, I agree with you. I think it's the complexity in processing secondary materials from secondary resources is similar to mineral resources, where every deposit you really need to look at in detail individually, because every deposit is different from another. So like you say, every case of recycling this particular phone is different than another one or such like that. And so it would be nice if there was one solution which solves all problems, but it won't be. There's a lot of work to do to find what the best solution is for each individual case. And it's important that we, as you say, communicate that to the policymakers and also to the general public, because in the end, the general public is the one who votes for these politicians or not. Yeah. So
that's the idea. That's why we had this recycling label, which, by the way, is gleaned from the energy label. As you said, energy label is very symbolically linear with its gradients. So we said, okay, let's put it on its head and just turn it so it's circular.
Yeah.
But you'll be surprised people don't want to see that, because the stories that have been said up to now, how do you retract from back into the truth domain?
yeah, that's the shame of it. There's been so much exaggeration.
It's difficult.
Yeah,
Yes, it's difficult.
That's not true. Yeah.
And that's problems, but I'm slowly chiseling away at that with all these examples that are happening.
Yeah.
And trying to bring it to the public domain, and also having young people to go out with the message. I can't just say, well, there's nonsense. I say, okay, here's the simulation model. This is the reason. Okay, this is real. And that's what I think good engineering schools should be doing. Teaching young people that type of detail. But also the problem with with these modern products, and that's what we've been trying to explain over years as well, is vis-a-vis minerals, which are sort of geologically, geochemistry related, whereas if you're looking at sort of design products, they are functionally brought and glued together to create this functionality, and so they're not really compatible chemically seen. And that's the issue. So by just that mere fact, to unmix this sort of shotgun marriage of materials and taking it apart again is just too difficult, and that's where we have our issues.
Yeah.
So, but what I would like to also convey is, whereas the materials or the minerals processes are dealt the nature card, the product designers and the secondary are dealt the cards by the material scientists. But there's for me still a too large gap between material science and processing to fully understand, okay, we'll get our high impact factor journal publication on some new material. But then I always ask, what the frigging hell is this going to do to the cycle? And as Peter said, yeah, what is those inevitable residues I will create somewhere in a heap that I have to deal with? And they will land at the metallurgist's backyard. And then we get the bad name because, yeah, we're not dealing with all the residues. But it is the designer of material, the product designer, that is dealing us as processes with that card. And so we can intensify processes to take it apart. But the treasure project I mentioned is trying to bring that message back to the designer and say, hey, this is your design consequence, this heap of rubbish, which we cannot deal with, and take note. And so we need to also, coming back to Peter Scales' question, how do we get this working? Circularity means communication between all disciplines as well. And in that, lowering the barrier of entropy, or exergy dissipation between just discussing stuff at the interface, where people don't want to listen to each other, is actually making that more streamlined, will also help very much. And that's a social sort of behavioral type of science issue. Yeah. Which would be beautiful to interact as well with this discussion.
Yeah. Well, let's leave it at that. Thank you again very much, Marcus, for a nice talk.